Let's move ahead by talking about mean, variance, covariance, and correlation. And again, this is just so much at the heart of finance, and in particular at the heart of portfolio theory, that this is stuff that you should be mumbling about this in your sleep, right? So anyway, what we're going to do is we're going to have two assets here over 3 years. So this is our sample period. We're going to calculate the mean. We're going to calculate the variance, the covariance, and then ultimately the correlation. And this correlation is what I frequently refer to as the mother concept in finance. So remember, the mean gives us an idea of the center of the distribution. Variance for one asset or the other tells us about the volatility. So the higher the variance, the greater the risk or the greater the spread of outcomes. Okay? The covariance tells us how these two things move together. But remember, covariance is a unitless measure. So it's bounded by positive and negative infinity. So if you tell me the covariance is 49, well, all I know is that that's positive. That means they tend to move together, okay? And it's less strong co-movement than if it had been 50, right? So covariance is difficult to interpret. It's mathematically fine. It works and plays well with other components of our portfolio optimization process, okay? But just interpreting it is difficult because it's in the units of observations. Correlation is a unitless measure. So it takes the covariance and it brings it down to this thing that's going to be bounded by -1 and +1, right? +1, perfect positive correlation. -1, perfect negative correlation. Positive, they go up and down together. -1, they go exactly opposite direction. Correlation of 0 means there's no identifiable linear combination, right? So this is just ground zero for portfolio building, so let's make sure we know what's going on. So here we have two assets, A and B, 3 years sample. So asset A, 5% -2 and then 12%. Asset B, 7% -4 and then +18. So the first thing we can do is calculate the mean return, and if somebody asked for the average return, well, averages can be geometric averages or arithmetic averages. There's other ways to do it, but typically when someone says an average, what they are referring to is the mean or the arithmetic mean of the sample, and that's what we're going to use here. So for the asset A, we're just going to add up those three returns: 5%, -2, and 12%. That's going to give us 15%. We're going to divide that by the number of observations, which is 3, and we're going to get an average return of 5%. For asset B, we're going to do the same thing, add up the 3 returns, divide it by 3, and we're going to get 7%. So the mean return for asset A is 5, the mean return for asset B is 7. All right, so that's means. Let's move on and talk about variances. Okay, well, remember, variances, we talk about volatility about the mean. Volatility about the mean. So what we're going to do is we're going to take each outcome. So looking at asset A, we're going to take the outcome in the first period. So that's going to be, I'm going to call it R, okay, I, and we're going to subtract from it the mean, right? So I'm going to call it R bar. So we're going to see how that return varies from the average. Now, if we did this, and we're going to ultimately sum this up, okay, over all I. So we're going to do this for all 3 observations. So we're going to take the mean, the observation minus the mean. So we would have 5 minus 5 for the first one, and then we would do -2 minus 5 for the second, and 12 minus 5 for the third. But if we just did it like this, okay, we'd always be trending back to 0, because some things are higher than the mean, some things are lower than the mean. So what we could have done is we could have just taken absolute values, okay, so that would have been the absolute deviation, which is a perfectly acceptable measure of volatility. It just doesn't have good mathematical properties. So instead, we're calculating variance, which means we're going to take the deviation from the mean for each observation, and we're going to square it. Now they're all positive, right? So the summation means we're going to take the deviation from the mean for each observation, square it, and then we're going to divide it by n-1 because we're working with a sample. If this were a population, we divide by n. This has to do with counting theory that underlies this, but remember, you're almost always going to be using n-1 unless they say this is the population, which I've never dealt with a population in my career, but I suppose on the CFA exam we could see it. So we're going to take the deviation for the first observation. It's 5%. The mean is 5%. So 5 minus 5 squared. That's going to be 0. We're going to take -2 minus 5, so that's going to be 7 squared, so that's going to be 49. We're going to take 12 minus 5 12 minus 5, so that's 7. We're going to square that. That's going to be 49. Then we're going to divide all that by 2 because that's n-1, and that's going to give us this give us the variance of of asset A, given for the sample period. So this is the variance. The problem is that number is in units squared, right? So when do you go around talking about things in units squared? Well, maybe if you're at your high school reunion and you're talking about how much money you make, you say, I make, X thousand dollars squared. Anyway, or something like that. But normally we want to talk about things in units, not in units squared. So to get to the standard deviation, okay, we're just going to take the square root, okay, of the variance. So take the variance here, that's sigma squared. That's going to be the standard deviation. So in this case, it's going to be 7%. We do the same thing for asset B, and we end up with a standard deviation of 11%. So asset A has a lower return and a lower standard deviation. Asset B has a higher return and a higher standard deviation. That shouldn't surprise us, right? Okay, so that's mean variance and standard deviation. Now let's talk about covariance, right? So for covariance, when we calculated the variance, we took each outcome, okay? So we took 5 minus 5, right? And then we squared that, and then we took the second observation, 2 minus 5, and squared that. Well, now we're not interested just in the volatility, we're interested in how these things co-move, right? So we're going to take the observation in each state of the world and subtract off its mean in that state of the world, and then we're going to multiply that by the difference, the deviation from the mean, for the other series. So we're going to take 7 minus 7. So this is going to end up being 0 minus 0 in the beginning, right? But that is, we're looking at the product of the deviations from the mean for both series. So this is for asset A and this is for asset B in the first year. This is asset A in the second year. This is asset B in the second year. And then asset A in the third year and asset B in the third year. So notice what we're actually calculating here. If both series are above their mean, then they have two positive numbers, and the product of two positive numbers is going to be positive, right? If they're both below their mean, okay, then we've got the product of two negative numbers, but a negative times a negative is also going to be positive, right? So the product of the mean deviations here, the product of deviations from the mean, that's the product of deviations from the mean, is going to be positive if they're above the mean together or below their mean together. The only time that's going to be negative if one is going up above its mean, the other is going down below its mean. Okay, well then we're going to get a negative value. So we're looking at how these things vary relative to their means, okay, in terms of co-movement. So we're going to do that, and once again we're going to divide by n minus 1, and I'm going to get rid of some of this chicken scratch. And in this case we're going to get a covariance of 0.0077. The problem again is that, all right, I know that number's positive, right? 0.0077, so that tells me they tend to move together. But I don't know what that means specifically. If you had told me it had been 0.009, that's greater, I would have said, oh, well, the co-movement is greater here, but I still don't know what that means, right? It's very difficult to interpret a covariance directly other than the fact that it's positive or negative, but it is easy to take a covariance and convert it into a correlation. This is certainly a formula that I would want to know going into the exam. That is that the correlation between two number series here, this could be stock A and stock B, it could be, sunspots and yak milk production or anything else, right? So we're just correlating two number series. Okay? The correlation is going to be the covariance between the two assets divided by the product of their standard deviations. So we calculated the covariance to be 0.0077. We know the standard deviation of asset A is 0.07, for B is 0.11 because we calculated those. When we take this product, what we see is that these two series are actually perfectly positively correlated. They go up and down together, actually by some sort of fixed scalar, but anyway, so they're going up by the same magnitude relative to their mean and down by the same magnitude relative to their mean together. So these are perfectly positively correlated assets, which are going to be sort of the end point if we're thinking about portfolio diversification. So when we get this, okay, we are going to say if we pick two securities and we find that they're perfectly positively correlated, that's going to end up making us feel a little bit cheated. So anyway, so that's mean variance, standard deviation, covariance, and correlation, and I would certainly make sure that I had a handle on that. Risk aversion, so this is an important important concept. Okay, and risk aversion just means that investors prefer less risk to more risk. So it doesn't mean that we necessarily minimize risk or that we won't accept risk. But we're going to trade off risk against return. So if we have two assets, okay, they both have an expected return of 5%. I want the one that has the lower risk. Okay, so and if you want me to buy the other asset, the one with the higher risk, you're going to have to give me a higher return. So two investments have same expected return. I'm going to take the one with lower risk. Okay, if they have the same risk, okay, then of course I love return, right? I'm going to take the higher expected return. So I'm non-satiated as an economic principle. I want more, right? That's what's going to make me happy in the economic model, which is kind of a sad thought. But anyway, more stuff is going to make me happy. But nonetheless, if the risk is the same, I'll choose the higher expected return. If the return is the same, I will choose the lower risk. So because someone is risk averse, and the language they use this a little bit, there's some variability in the way the language is used, but the fact, if you say somebody's risk averse, well, that's like saying, they take in oxygen and give off carbon dioxide. Okay? Yeah, everybody's risk averse. The question is your risk tolerance. You can be more or less risk tolerant, but we're all risk tolerant within this risk aversion parameter. So we would all prefer more return to less. We all prefer less risk to more. So the fact that we're risk averse doesn't mean we choose really low risk portfolios. It just means that we have to be rewarded more in order to take on more risk. And we'll see this play out as we go through our portfolio and capital market theory stuff.